So heat is the transfer of thermal energy, and this occurs due to temperature differences. Temperature is the measure of thermal energy in a system, the measure of the kinetic energy of the particles. So we know from just regular experience that heat flows from matter with a high temperature to matter with a low temperature, and that heat will flow until both things are at the same temperature. We call that thermal equilibrium. They're thermally equal, right? And after that, there's no net transfer of heat. So you think about a hot cup of coffee and you put some ice cubes in it. Does the coffee get hotter? No, it gets colder. Heat is being transferred from the hot coffee to the ice cubes to melt them into water and heat the water up. The coffee gets colder, right, until it's all at the same temperature. So when a system absorbs heat, its temperature changes. And the temperature increase is directly proportional to how much heat it absorbed. So when two things are proportional, there's a proportionality constant. And the proportionality constant here is called the heat capacity, or capital C. So this is the heat absorbed, and this is the change in temperature. And they're proportional by this proportionality constant. So heat capacity can be defined as the heat required to change the temperature of a system by 1 degree Celsius. The larger the heat capacity, the smaller the temperature change for a given amount of absorbed heat. But the heat capacity is going to depend on the amount of matter. A big chunk of something is going to take more energy to heat up than a small chunk, right? Heat capacity depends on the size of the object or the system. So we say heat capacity is an extensive property. It depends on the size. Well, that's not as useful. Makes things a little more complicated. So the one we use more often is called the specific heat capacity. This is an intensive property. It's the intrinsic capacity of a substance to absorb heat. So the heat capacity depends on the amount of stuff. We can get around that by using the specific heat capacity. And that both of those are going to depend on what the stuff is. Some things heat up faster than others. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram by 1 degree Celsius. So now we're specifying the mass. That's the one we use the most. We'll also sometimes see a molar heat capacity. So that's the amount of heat needed to raise the temperature of 1 mole by 1 degree Celsius. So the units for specific heat capacity are joules per gram degree Celsius. For molar, it's joules per mole degree Celsius. These are intensive properties. Like density, they can be used to identify a substance. So here's the equation. Q equals mc delta T. Q equals mc delta T, and sometimes students call that MCAT, because the MCAT is the test that you dread if you're trying to go to medical school, but this kind of looks like CAT, MCAT. That helps you remember it, great. So Q is the heat in joules, M is the mass in grams, C sub S is the specific heat capacity with units of joules per gram degree Celsius. The temperature change is measured in degrees Celsius. So if we look at the units here, we get joules is equal to grams times joules per gram degrees Celsius times degrees Celsius. And these units cancel out, and we get joules is equal to joules. So the units on the specific heat capacity are just so that all the units work out. You do not memorize specific heat capacities. So you look them up or you are given them. Okay? On an exam, they'll be given either in a separate table or in the problem itself. Homework and worksheets, oftentimes they won't say anything about it, and you have to go look it up. Pretty much anything you need is going to be in this little table here. So these are different substances. There's some elements, some compounds, and then these are materials. They're mixtures, sand, glass, granite. And if we look at the values here, lead, very low, 0.1. Gold is also very low. Here, aluminum is higher, 0.9. But the very highest is water, 4.18. That's more than 4 times the heat capacity of anything else on this list. Water has a very high specific heat capacity. That high specific heat capacity means that water can absorb a lot of energy with only a small change in temperature. And that can be useful in a lot of situations. So water is commonly used as a coolant because it can absorb a lot of heat and move that heat to somewhere else without changing the temperature very much. So that's why the radiator fluid in your car is mostly water, because it can absorb a lot of heat generated by the engine and move it to the radiator where it radiates and gets dispensed into the atmosphere. The high heat capacity of water also has a big effect on our climate. So if you think about the weather in Fresno compared to, say, the weather in San Francisco, right? Where's it going to be cooler? San Francisco, yeah. Are they that much farther north of us? I mean, we expect it to be cooler in Alaska, right? Because the farther north, or when you get really close to the South Pole, it's going to be colder, further from the equator. They're only a little bit north of us, but it's a lot cooler there. So common temperature in Fresno in the summer, 100 degrees, that seems kind of nice, right? It's like, oh, that's not bad. Remember 115, right? 100 is nice compared to that. The San Francisco might be 68 degrees when we're 100. Why? Water. San Francisco is on a peninsula, surrounded by the San Francisco Bay and the ocean, right? So as the sun beats down and heats things up, the water absorbs a lot of that energy without changing its temperature very much. It's like you go swimming, in the summer, and the concrete around the pool is super, super hot, right? Is the water that hot? No. It's been in the same condition, the same place as the cement, but the cement got a lot hotter. The cement has a lower heat capacity. So for the same amount of energy absorbed, its temperature changes a lot. The water in your pool doesn't change its temperature very much. So during the day, the water absorbs a lot of this energy, which prevents the temperature from getting too high. And then at night, it's releasing that energy because now the air is cooler than the water, and so it keeps it from getting colder. So common temperature, daily variation in San Francisco might be 10 degrees. 68 during the day and 58 at night. And here, 100 during the day, 60 at night, right? That's entirely possible. 40 degrees, because we live in a desert. That's why. Okay, so let's use that equation. Again, whole bunch of words here. We're going to read them. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. Yeesh. Okay, first of all, what would be a much easier way to figure out if this is gold, chemistry-wise? Density? So you can measure the mass. Measuring the densities, the volume's easy. Take a graduated cylinder with some water in it, right? stick it in there and see how it changes. But sometimes we want to do things the hard way. Okay, so we've got numbers. There's a number, here's a number, here's a number, here's a number. And then it says it's not a question, it's a command. Find, do it. Find the specific heat capacity. Well, write down these numbers. 4.7 grams, 57.2 joules, 25 degrees Celsius, and 57 degrees Celsius. And then let's label them, right? So gram is a unit of mass, and the problem also tells us that this is the mass. So I'm going to call that M. And it says it absorbs this much heat. And what's the letter we use for heat? Q. And then these are temperatures, right? So that would be a T. We have an initial temperature and a final temperature. We could do T1 and T2, but for whatever reason, they do TI and TF, initial and final. IT, yeah. So it rises from this to that, right? So this is the initial, this is where it starts, and that's the final. So TI, initial temperature is 25, and the final is 57. And it's asking us for the specific heat capacity. Well, there's an equation for that, right? Q equals mc delta T. This C sub S is the specific heat capacity that we're trying to find. So we're going to take the... Okay, who knows where I left off, but there we are. If there's missing things, you can look at the Monday, Wednesday lecture. Any questions about this? There's something I'm doing that's causing it to pause like that, but I'm not sure what it is. Okay, so if we have two objects at different temperatures and they're touching each other, heat will flow from the hotter one to the colder one, right? Until they reach the same final temperature. The amount of heat lost by the hot material is the amount of heat gained by the cold material. So we can define one of those things as the system and the others as the surroundings. And so we can say that Q for the system, whether it's positive or negative, is equal to -1 times Q for the surroundings. If you took absolute magnitude, they're the same number. The negative sign just tells us which one's losing and which one's gaining. So we did those other problems, and this, it talks about the student saying, well, it gained this much energy, or it lost this much energy. How do you measure that? That's actually not super straightforward. The best way to measure it is to do something like this, where you've got a beaker of water, and you put your hot object in there, and you measure the initial temperature of the water, and that hot metal is going to cause the water to heat up, right? And you measure the final temperature of the water. And then you know the change in temperature for the water. And you look up the specific heat capacity for the water, and you measured the mass of the water. So you can calculate how much energy went into the water, and that is equal to the amount of energy that left the metal. So maybe you don't know what kind of metal that is, but you know its initial temperature. Maybe you had it in an oven or something at 55 degrees Celsius. Its final temperature is going to be the same as the water. So you can calculate delta T quite easily. You can find the mass of it, and so then you can calculate the specific heat capacity, because the energy lost by the metal is equal and opposite in sign to the energy gained by the water. Any questions? So a block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? So this is one of those problems where it might be helpful to draw an ugly picture. So here's my ugly beaker with my ugly water and my ugly copper block. There's a theme here. Okay, that's copper. It's copper colored, right? So that's kind of, giving us a mental picture, however ugly, of what's going on. And let's highlight our numbers. And that's all of them. So let's write those guys down. I'm going to use purple because I like purple. So I've got 65.4 degrees Celsius. I have 95.7 grams. I have 22.7 degrees Celsius. I have 24.2 degrees Celsius. So what we're looking at here is that Q for the copper is equal to Q for the water, but the sign is different. So we're going to have two specific heat capacities and two masses and two delta T's. So we kind of have to indicate which ones we're talking about. When I did this example yesterday, I used different colors for those numbers. Here I'm going to pretend that I'm like a student with a pencil and I don't have multiple colors, even though I have lots and lots of colors. This obviously is a temperature, right? So that's T. What do we know about that temperature? It's initial. It's the initial temperature of what? The copper. So we'll call that T sub I, comma, Cu, initial temperature of the copper. And it's immersed in a beaker of water containing this much water, right? So that is a mass. That is the mass of the water. Beaker containing this much water at 22.7. So this is the temperature of the water, right? So that's temperature of water. Is that the initial or the final temperature of the water? The initial. When those two substances reach thermal equilibrium, the final temperature is 24.2. So this is the final temperature. Of which thing? Of both things, right? They come to the same temperature at the end. So that's the temperature for the copper and for the water. So I'm just going to call it TF. So we can take this idea here and we can solve this problem in two different ways. We can say, well, okay, Q for the copper is going to be mass of the copper times the specific heat capacity of the copper times the change in temperature for the copper, and that's going to equal negative mass of H2O times specific heat capacity of H2O times the change in temperature for H2O. I ran into the beaker. And what are we trying to find? The mass of the copper. So the thing we're trying to find here is this guy. So we could use this as one giant equation, rearrange it, and plug things in. That's how I did it yesterday. So I'm going to do it a different way this time. So what I'm going to do is I'm going to calculate QH2O, because that's not the thing I'm trying to find anything about. So Q for the water is equal to M for the water times the specific heat capacity for the water times the change in temperature for the water. Okay, well, we know what the mass of the water is, right? 95.7 grams. Specific heat capacity. To look that up. I remember this one, 4.18. So you go look that up. It's 4.18 joules per grams degrees Celsius. And then the change in temperature for the water, delta T for the water is the final temperature, 24.2, minus the initial temperature of the water, which is 1.5. So 95.7 times 4.18 times 1.5. 600.039. The grams have canceled, the degrees Celsius have canceled. That is joules. How many sig figs? 2, because of the temperature. The temperature change is subtraction, and so we're going with number of decimal places. They both had 1 decimal place. So we do the difference, we still have 1 decimal place, and that's 2 sig figs. So that's Q for the water. Well, Q for the copper is equal to negative Q of the water, right? So that's going to be negative 600.039 joules. So I can take this is equal to, actually let's just do it, where's the weight here? Get rid of that. So this is equal to Q for the copper, right? Q equals MC delta T. Mass of the copper, specific heat capacity of the copper, change in temperature for the copper. So we're going to solve this equation for the mass of the copper. So the mass of the copper will equal Q for the copper divided by the specific heat capacity for the copper times the change in temperature for the copper. We used the water information to find out what Q for the copper is. It's negative 600. Joules. Does that negative sign make sense? Yeah, because the copper was hot and it's losing energy to cool down. So that's the Q. We have to go look up the heat capacity for copper. I actually remember this one too. It's kind of scary. 0.385 joules per gram degrees Celsius times the change in temperature. Well, this one's going to be different. Let's maybe squeeze it in over here. Delta T for the copper. Again, it's the final temperature minus the initial temperature. The initial temperature of the copper is 65.4. 24.2 minus 65.4 equals negative 41.2. That means the temperature of the metal went down, and that's consistent with what we understand is happening in this problem. So negative 41.2 degrees Celsius down here. Again, be careful when dividing by this product. So I have negative 600.039 divided by, open parentheses, 0.385 times negative 41.2, close the parentheses, equals 37.83. I'm going to have 2 sig figs because of that guy. And that's going to be grams. And so the mass is 38 grams. Why they didn't just use a balance is beyond me, but then we wouldn't have an example to do. Any questions? So that was heat. We have to talk about work as well. The work that applies most specifically to things that we're doing in Chem 3A, Chem 1A, is pressure volume work. And so this is what happens when a force that's caused by a change in volume acts against an external pressure. So like a balloon is expanding and pushing something, right? When gases expand, delta V is positive. They get larger. But that system is doing work on the surroundings, and so the work has to be negative by our sign conventions. So the work is equal to negative times the external pressure times the change in volume. Change in volume is a positive number. The pressure is a positive number, but because the work is being done by the system, not for the system, we need to make it negative. So we just slap a negative sign in there. And this is the sort of work that happens in an internal combustion engine where combustion happens inside your engine. So you have this little explosion that causes the gases to expand, and they push against the piston. And that's what ultimately causes your car to move. The units we end up with here, pressure in atmospheres times change in volume in liters, we get atmosphere liter, which doesn't sound like an energy unit, does it? It actually is. We can convert that to joules using this guy here. 1 atmosphere times liter is equal to 101.3 joules. I don't expect you to remember that, but just try to remember there is a conversion. Okay, another cylinder equipped with a piston. It expands against an external pressure of 1.58 atmospheres if the initial volume is 0.485 liters and the final volume is 1.245 liters. How much work in joules is done? Read the problem. Highlight the numbers. Oops, I missed one. Highlight the question. Wants work in joules. Pull out those numbers, write them down. 1.58 atmospheres, 0.485 liters, 1.245 liters. So as I'm looking over your worksheets, I see that some of you are totally nailing it. Awesome. And some of you are a little confused, right? You're getting a little lost. But I don't see you doing this. So you don't have to use this method if you have another method that works for you. But if you don't have a method that works, try my method. Just give it a try. Write the numbers down, label them, identify what you're starting with, what you're trying to find. Always write the units. Okay, so I've got this pressure. Let's call that P. And then I have 2 volumes. The initial volume is this, right? So I'm going to call that the initial volume, and the final volume is 1.245. So I've got final and initial volume. The relationship here, the equation, work is equal to negative pressure times change in volume. Delta V, the delta means what it always means, final minus initial. So V is V final minus V initial. So 1.245 liters minus 0.485 liters. .760 liters. I wrote that 0 in because both of these numbers have 3 decimal places. So my answer should have 3 decimal places. My calculator doesn't understand that, so we have to make allowances. So the work is equal to -1 times the pressure times the change in volume So work is equal to -1.2008 atmosphere liters. Question wants it in joules. So I'm going to take my 1.2008 times 101.3, and this should have 3 sig figs. So this is going to be, it's 121.64, so 122 joules, and I forgot the minus sign. The work is negative because it's doing work on the surroundings. Any questions? There's another one. I think this is the last one. Yeah, last one for today. When fuel is burned in a cylinder equipped with a piston, the volume expands from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. In addition, 875 joules is emitted as heat. What is delta E for the burning of the fuel? I read the words, mostly. Highlight the numbers. Highlight what I'm trying to find, delta E. Write down the numbers with their units, 0.255 liters, 1.45 liters, 1.02 atmospheres, 875 joules. The volume expands from this to that. So this is initial and that's final. Initial volume, final volume. This is our external pressure, so that's P. And heat, that's Q. Now the question is that positive or negative? The heat is emitted. It's negative, it's going out, right? If you emit money, just walking down the street and $10 bills fly out of you, you're losing money, that's negative. And I put the equal sign too close. There we go, so that's negative. So it's asking us for delta E. So, we need some relationships here. We can go looking for equations. We know that delta E is equal to Q plus W. And we also learned that W is equal to negative P delta V. So let's calculate W first. W is negative P delta V. So the pressure, we have negative there, and 1.02 atmospheres. And delta V is 1.45 minus 0.255. $1.285. liters. I'm underlining the 8 because this one only had 2 decimal places. Nope, that wasn't the 8. There's the 8.
You wrote the final volume, so 1.54.
I did. Thank you. That can happen pretty easily. So let's go back and fix that. 1.45 minus 0.255. Doesn't do that. 1.195. That's better. Times negative 1.02. So the work is equal to negative 1.2189 atmosphere liters. So I'm going to take my work and add it to, oops, didn't mean to do that. I'm going to take the work and add it to the Q. What's the unit on Q? J, joules. That means I need to convert this to joules. So I'm going to multiply by joules and divide by atmosphere liters. And the relationship is 1 atmosphere liter is 101.3 joules. So I'm going to take that number and multiply by 101.3. Negative 123.47 joules. So delta E is equal to Q, negative 875 joules, plus W, negative 123.47. Here we're adding, subtracting. This has is in the ones place, no decimal places, and so that's where my answer is going to end. Minus 998.47 joules, or minus 998 joules. And this is a really reasonable scenario. So we got 998 joules of energy out of the combustion of this fuel. But we only got 123 joules of work out of it. The rest of it went to heat, which just made the engine hot and was annoying. Any questions? Minus 998.